All right, we're almost done with rotation. Rotational energy here now, and then we would have momentum would be next week, and then you guys have seen everything that would be tested for the year. So linear kinetic energy, or translational, is 1/2 mv squared. So then we just replace our variables. M is now moment of inertia, or I, and V is now omega. Right? So everything is the same. This is the old way that I used to do problems, but now it's very similar. Remember our LOL diagrams? Okay? So that's the energy that you start with. Right? So it's just any of these types. Remember, you have potential energy if you have a height. You have spring potential energy if you have a spring compressed or extended. You have kinetic energy if it's moving. You have rotational kinetic energy. Is it rotating? Okay? And so that's when you have rotational kinetic energy. We never used the term work non-conservative this year. We said, was there work external to the system? Then over here, same types of energy. Before I jump into that, remember, work external gives you a change in energy. And so with rotation, you have to, with a work external, you need to change speed. That's the way that your energies are not going to be the same as if you have a force that's actually changing speed, taking speed away from the system or adding speed to the system. So that's back here to work. Remember, force that is parallel to distance that changes speed, that's a force that does work. Again, I don't like that equation because people just randomly use that angle. So this equals a change in kinetic energy. So this equals a change in rotational kinetic energy, a torque through an angle. So only forces that speed up or slow down do work, where on the other side, only torques that speed up or slow down do work rotationally. If they were to ask for what is the omega final of this, this is how you could put them all together. So I know, if I want to know the omega final for a torque, well, I could say torque times change in theta equals change in K rotationally. So the man would be pushing, and he's definitely creating a torque, times the radius, times the change in theta, equals 1/2 I omega final squared minus 1/2 I omega initial squared. Okay, so then those are the information that you'd have to have. You'd have to know his force, the radius. 1 revolution we know is 2 pi radian, so you could plug that in there. And you'd have to know the moment of inertia for this problem to solve that. So that's one way you could go about doing it. So now, let's take a look here and look at things going down the hill. They will do this a lot, so they'll race different things down a hill, and they want to know which one gets there first. Right? So let's talk about, so here, sorry about that, we want to see a hoop and a cylinder and which one reaches the ground first. And we can look at this in terms of energy. So I talked about, as we're going down, here we could do energy as you're changing a height. So let's think about the energy at the top. Okay? So the energy at the top, the first location, it's not moving, it only has a height, so I start with UG. My system is we'll call that the object and the earth. Because remember, gravity only, you only have gravitational potential energy if you factor the earth in there. So then, as it's going to go down, what type of energy do I end up with? Well, down here, it definitely has a linear velocity. So at the other location, I have kinetic energy, but do I have rotation? And so let's think about this. My forces, I got gravity, normal force because it's perpendicular. So if these were the forces, do either of these create a torque? The answer is no. They both go through the axis of rotation, so those do not create a torque. So where would friction go? Well, this now goes to the rolling friction that we just talked about. Acceleration is this way, and I need rotation that way, because friction always has to fix that. So friction must go up the ramp to get that rotation going. So then I would have rotation. So then this is also K rotationally. Now, typically before, when there was friction, we had work due to friction was either going in or out of the system. But the interesting thing here is work from how can I write that? Force of friction static equals 0. Why? Because we saw earlier that static friction, force of friction static, only changes direction. This is not speeding it up or slowing it down. Okay? All it's doing is causing this rotation, so it's not actually changing our energy, and it's actually just changing type. So by this happening here, it's not taking energy out of the system, it's taking energy that was gravitational potential, and it's turning that into rotational kinetic energy. So energy is still conserved in this situation. No energy is being added or removed from that system. Right? And so that's what the setup is. For a disk, nothing else changes. Both of them starts with potential and goes to rotational. So both of them would look like this. Let's say I start with this much. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then afterwards, let's just make up some numbers. Let's say it's 3 and 3. This is for a disk or any object rotating down. Now, a common problem is they'll do a sliding box without friction. They'll ask you to compare those. So what if I have a box without friction? And so there the answer is, on this one, if there's no friction, there's nothing to cause it to rotate, so it's going to have all this translational energy. So if I have more in a race, if I have more kinetic energy, and between these two, I have more kinetic energy, and kinetic energy is 1/2 mv squared, and we'll come out final is all we're looking at, is that means I have a greater, if I have more linear kinetic energy, I have more final velocity. So then that also becomes a greater velocity average, so that wins the race. So without friction, the block is always going to win. And that makes sense because friction has to go up the ramp to make these things rotate. So it's kind of like friction is slowing it down. But instead of slowing it down, what friction is doing is it's taking some of that potential energy and it's converting some of the energy into rotational kinetic energy. So not all of it gets transferred into that linear movement. And so that's why these different objects lose. Now, why does the hoop lose? Okay? Well, what's the difference between a hoop and a disk? Okay? Well, that is their I, their moment of inertia. And which thing is harder to rotate, a hoop or a disk? And the answer should be a hoop. A hoop is harder to rotate, so it takes more of the energy to get this thing to rotate. So then it is going, rotating, has taken more of that rotational energy. So for a disk, versus, let's say, if we compared this and was looking at a hoop, okay, the hoop, if the disk has 3 bars of rotational kinetic energy, let's say maybe the disk has 5 bars. So then there's hardly any rotational energy. So there's a lot less. And so it's actually pretty cool if you were to go and look at these things that you can find out the only thing that matters in the race is the shape of the object. No matter what happens, the only thing that matters is the shape, and I'll post another video, but I'll show you why. So let's look at this. This is mgh, 1/2 mv squared plus 1/2 I omega squared. Let's get these all into linear variables. So mgh, that's all linear, plus 1/2 I, let's call that k mr squared because it depends. Remember, k is the shape of the object. Now we want to turn omega into linear. So remember, angular times r equals linear. So omega equals v over r. So for this, I'm going to put v over r, but then I have to square it, so I square both of these terms. So those cancel out. So now I'm left with mgh equals 1/2 mv squared plus 1/2 k mv squared. Oh, mass in every term, they cancel. So let's solve for v. I'm going to try and isolate it. So I have gh equals, I'm going to isolate out the v squared. So I have v squared. And then here I have 1/2. They both have a 1/2. I'm going to isolate it out here differently. I'm going to isolate it out. 1/2 v squared, and this is 1 plus k. So then if I wanted to solve for v squared, I would do gh over 1 plus k. I got to get rid of the 1/2, so this is going to be multiplied by 2 equals v squared. To get rid of that, I could square root it. So this tells me to find out who's going to win the race, what matters right here, g and h. So they all have the same g, they all have the same h, so the only thing that matters is k. So that's pretty cool. Winning the race, the only thing that matters is the shape of the object. Objects with a higher rotational inertia, that's just which ones are harder to rotate, have a higher k value, so the hoop is always going to lose because it has the highest k value, and this is your ranking of your values. If the k value is 0, it doesn't rotate at all, then, well, not 0, you're going to have nothing down there, just the 1. So then you are going to go the fastest. So that's why the sliding box would win, because it's just going to have the 1 on the bottom there, not a smaller fraction there. So that is rotational kinetic energy. Hopefully you can go play with that, and you just really got to try and see what you can solve. Good luck.